Today we derive the famous Lagrangian equations of motions. Now at first we record the D'Alembert principles. Sum of, actually first we write the mathematical expression sum of I equals to 1 to up to n FIA, that's called applied forces, minus MIRI double dot and the virtual displacement del Ri equals to 0. That states, which asserts that the work done by the applied forces here and work done by the inertial forces here in a virtual displacement is 0. This is the main things for D'Alembert principle. Now with based on this principle we step forward. Let's see what's happened. Now the virtual displacement del Ri, then the work done by the applied forces for if we are taking this way the equations del WA, that is the work done by the applied forces, is equal to sum of I equals to 1 to up to n particle system Fi in del Ri, where del Wi is this quantity. And now exactly balance the work done by the inertial forces is del W inertial, that will be sum of I equals to 1 to capital N Mi Ri double dot del Ri. If we take it equation number 1 and this is equation number 2 and this is equation number 3. Now considering here in particle systems, that's a holonomic n particle systems considering. With n degrees of freedom. Then 3n coordinate systems can be expressed in terms of in generalized coordinate Qj, j runs from 1 to up to n. Now here Ri equals to, Ri is the function of Q1, Q2 up to Qn and T, and taking the equation number 4. And it's clear that every I, that is the n particle system 1 to up to n, where I equals to 1 to up to n. Now the virtual displacement, the time is treated to be frozen, that's a frozen time, and as a result the displacement of variation del Ri, if we treat time as frozen, so it will be no part of time t. So j equals to 1 to up to small n del Ri del Qj and virtual displacement for I equals to 1 to up to n. Now taking it equation number 5. Now putting 5 into then del Qa is the form of del Qa is equal to the applied forces. If we plot it in number 2, that's here del R, so that will be sum of I equals to 1 to up to n FIA, that is substituted del R, and for here it is FIA and sum of j is equal to 1 to up to small n del Ri del Qj and del Qj. In this way and in this way we find sum of, here it is continuation of the earlier pages, I of is equal to I of 1 to up to n. Here it is FIA applied forces and del RI del QJ and if we taking an summation j equals to 1 to small n, and here it is del qj. So here will be j runs from 1 to small n, that is degrees of freedom, qj del qj. So we can take it equation number, here it is equation number 6, and where qj is equal to sum of I runs from 1 to capital N FIA del RI del QJ, taking it equation number 7. And these 6 and 2 are the two equivalent version of del QY, and the RHS of equation 6, that QJ appears attached to del QJ, which are the virtual displacement for generalized coordinates. QJ may be defined as generalized force. However, unlike the vectorial characters of the conventional force, it's a scalar in character. Now, if the system under consideration is conservative, that is, Fi can be expressed in the potential form Fia is equal to minus grad of V, that is a scalar potential, and V is the function of R1, R2 up to Rn and T. Then consequently we can write Qj is equal to minus del V del Qj. It's obvious and clear. That's Qj1 also derivable from the same potential. V is the function of Q1, Q2 up to Qn. Now, if we consider here del W inertial forces given by the 3, it can be written as del W inertial is equal to sum of j runs from 1 to small n, sum of I runs from 1 to capital N minus mi Ri double dot into del Ri del Qj into del Qj. If we consider here, it is number 8, so it will be number 9. And using 5 to handle the equation number 9 more effectively, we proceed to define two lemma. At first, we consider the kinetic energy of the holonomic system, T equals to half of sum of here you consider I equals to 1 to up to n mi Ri dot square. Now straightforward, it's clear and obvious result that del T del Qj dot, that will be equals to sum of I equals to 1 to capital M mi Ri dot del Ri and del Qj for j runs from 1 to up to small n, degrees of freedom. Now it's clear from the equation of Rj standard what Rj is there. Rj actually is a function of the coordinate q1, q2 up to qn here, or Ri, whatever maybe as the notation is. But if we find here where Rj or Ri is the function of the coordinate q1, q2 up to qn and t. And it is also possible, if we taking derivative of Ri dot, we have to find del Rj del qy into qy dot. So del Rj into del qy dot equals to del Rj del qy. So straightforwardly applying this condition and getting the result of these things. So it should be needed to prove it, and this result is useful to us, taking the result as equation number 10. And if we consider the operator commutative in the sense, that means ddt and del del qj are commutative. So ddt of del Ri del qj equals to del qj of dri dt, that is Ri dot. And from the RHS, its obvious and clear results, we find the part of RHS of the equations. Del del qj dri dt equals to del del qj dri dt, that will be equals to, if we take here sum equals to 1 to up to n, del 2 ri del qm del qj qm dot plus del 2 ri del t del qj. Taking del qj common, sum of m equals to 1 to up to n, del ri del qm dot plus del ri del t. So all these can be written as del del qj dri dt. Now prove the parts. Prove the part, it has 11. That is del del qj of this equation can be written as 11, the problem of 11. If we consider it as 11, we have to prove. We have already proved it. Next, combining 10 and 11, we get ddt of del t del qj dot is equal to sum of I equals to 1 to up to n mi ri double dot del ri del qj plus mi ri dot ddt of del ri del qj, that will be equals to sum of I equals to 1 to up to m mi ri double dot del ri del qj plus mi dot del qj, that's applying the commutative operator, and dri dt will be equals to ri dot. So it can be written as sum of I equals to 1 to up to capital N mi double dot del ri del qj plus del qj of sum of I equals to 1 to up to capital N half of mi mod of ri dot square. Now taking it equation number 12. Just a minute, we revise this equation. Sum of I equals to 1 to up to m mi ri double dot del ri del qj plus del t del qj, taking it equation number 12. Now it is clear from these equations. We are recalling delta inertia, that means substituting 12 in the equation number 9, we obtained del W, that is the inertial forces, sum of j equals to 1 to small n, sum of I equals to 1 to capital N. Recalling equation 9, mi ri double dot del ri del qj and del qj, that is the virtual displacement. Substituting this value, that is sum of j equals to 1 to up to n, it will be del t del qj minus ddt of del t del qj dot into del qj. Taking it equation number 13. Now representing 6, equation number 6, that is, if we rewrite this equation once more, that is del WA is equal to sum of j equals to 1 to up to n qj del qj. Rewrite the equation 6 once more, and here del W inertial forces, that is sum of j equals to 1 to up to n del t del qj minus ddt of del t del qj dot into del qj. Adding these two by the D'Alembert principle, applied forces and inertial forces will be 0, that is del WA plus del W inertial is equal to 0, that is sum of j runs from 1 to small n qj plus del t del qj minus del t del qj minus ddt of del t del qj dot into small displacement, that is virtual displacement, equals to 0. Now taking it equation number 14, and quantities del qj being arbitrary and independent, and from this result 14 that coefficient of each del qj vanish separately in the consequences, so it must be true that ddt of del t del qj dot minus del t del qj is equal to qj, where j runs from 1 to up to small n, and the moments, this equation, if we take equation number 15, is actually described the set of n second order differential equations involving n generalized quantities and their velocity for conservative systems, and when 8 holds, that means qj equals to minus del v del qj holds, where v is the function of r1 q, r1, r2 up to rn, that is velocity, r capital N and t, system of particles. And then this equation, that is equation number 14, equation number 14 can be expressed for the conservative form, that is ddt of del L del qj dot minus del L del qj equals to 0, taking it equation number 16, where L is equal to t minus v and v is independent of the velocities q1 dot, q2 dot up to qn dot, and L is called Lagrangian. And the equation number 14 and equation number 16, therefore equation 14 and 16 refer as Lagrangian equation of motion. Thank you.